Hi everyone, I'm Eddie Razgala and I'm with Thibault Cyril de Chezel and we will present you our method for the Ceteris Paribus challenge. So the aim of the challenge is to generate and edit some images, and for that purpose we mostly use StyleGAN2. So we will first present you inversion methods and then latent space exploration. With the images we generated, we applied some correction with a segmentation model, and then we will finally present you other methods we have found to explore the latent space and the choices we made about reality fidelity trade-off. So this is StyleGAN1. The main idea is the same than StyleGAN2, and it is to having a synthesis network that creates images, but having also a mapping network that creates a style vector that is applied to many levels of the generator. So to use StyleGAN2, we need to use inversion methods. So there are three types of inversion methods: encoder-based, that can encode all images, and optimization-based methods that needs to be trained on each images, and hybrid methods that combine both methods. Okay, we used encoder for editing Respository, and that encode the images and manage to generate style vectors that are close to the initial StyleGAN style vectors. And what we see in this slide is that compared to other approaches, they have lesser results. They have worse results in terms of FED score and distortion score, but in terms of when we see the images and many other images, we found out that even though they have worst matrix values, their inversion and their editings produce better images. So it shows that the metrics we usually use are not completely useful, and that do not completely reflect the human perception judgment. Okay, so we have found we have used the repository of the paper that introduced E4E encoder. It has a MIT license, so we can use it for any purpose, and it provides an E4E encoder trained on a FFHQ dataset with a StyleGAN decoder that come with. So let's talk about the dataset. We have 72 images to modify, and we have more than 25 attributes to find and study to change about all the images. So that's about more than 1,000 images to create. So we need automatic methods to transpose our images, and we need a fast meaning to explore the style space. I will first talk about the latent space exploration. Okay, to remind us, StyleGAN2 works with we have noise. We create a style vector that we duplicate into in order to applying to 18 levels of the synthesis network that also take noise and generates an image. And or if encoder for editing model takes an image, encode that image into a style vector that is directly of shape 18 by 512, and that style is made that in order that the reconstructed image is almost the same as the original image. Okay, and the first way to explore the latent space is to generate n style vector with the initial mapping network, and to apply a principal component analysis on those vectors. And we keep the repository we had gives us the 80 first components, and they say that is sufficient to explore the latent space. And with that components, we can apply it on each levels of the style the style of our image. So the edit state style is the initial style plus a factor multiplied by some PCA, some component. To efficiently explore our latent space, we made a user interface with Tkinter. So we load an image that we plot, and we plot the edited images. So we applied the transformation we talked before on the style vector encoded. And we show with the tick box on which level we apply this transformation and with which PCA. And that scale bar is in order to show the strength of the transformation. So here there is no change, so we just have the inversion. But when we apply, for example, the PCA 0 to level 4 to 9, we found out that we have a vector, a direction for in order to change the sex of the person. And with that same method, we could find directions for age. Now age should be double chin. We can create hair, make bands, change the skin color and the hair shape. Okay, and there is another method we used. We encoded all syllaba dataset. That is the dataset with many faces that are labeled with attributes, and they have the syllaba has all the attributes we want. And for example, when we compute the mean style vector of all persons that are men and the mean vector of all persons that are women, we make the difference between those two vectors. We expect that applying that new vector to the style of an encoded images, we can change the sex of that new person. To summarize, we encode our image and we get a style vector. We edit that style vector in order to generate a new image with the transformation we want. So we made another user interface with that new method. We can load 4 images and different vector we have computed before. So L0 is the main vector corresponding to the transformation we want to make, but we found out that some attributes are correlated with other attributes. And to decorrelate them, that is why we load other vectors in order to apply a correction on the main vector. Here I try to change to make people chubby or not, but we can see that it also changes the sex of the persons. So we load the vectors to change sex, and we applied a correction, and we see that in fact now we can make people chubby without changing their sex.
So with the previous method, we found vectors L1, L2, L3, L4 with their respective coefficient beta. But now we need to find alpha. And to do so, we found a method which is basically doing the scalar product between the style vector, the modified style vector, and the interesting vector. And we found that by fixing the same value for each image, we had which were as a human, which looked like for a human, like the same modification. So basically, if we set adult people to a projection of -40, we ended up with children that looked roughly the same age. And so basically, by doing the math back, we can compute a consistent value for alpha for each image, which made it interesting. Okay, so now we'll talk about another method we use to correct the former method. So the previous method has many advantages, such as the fact that the outputs are really realistic, at least in terms of the faces. But as we can see on this slide, there are many flaws, especially on the backgrounds, on the accessories, and sometimes on the hair, and basically in the overall shape of the face, there are some kind of flaws. So we tried a method to correct those flaws. And we did this by using segmentation algorithms. So by using the face parsing repository that is MIT licensed, so available on the internet, we basically isolate the missing the part we want to put back on the images. So here, for example, we want to put back the background, which we did. We added it, and then we cut it and add it back to the image. Now we see that there are some flaws still because of this method, because the semantic algorithm, the semantic segmentation algorithm, cannot take into account every obstacle in the image. So we did, for the sake of the competition and for the sake of our result, some Photoshop to improve our result. So that's about the correction part. Now I'll talk about a new method we came up with during the competition that we call the patch methods. Basically, what we found out about our encoder for editing is that it's an encoder that encodes images really close to the original StyleGAN2 latent space. In the sense that basically by sending any random image inside the encoder, its output decoded image always has some kind of realistic face. So we made an hypothesis that, as I said, the E4E encoder's outer space lies close to the StyleGAN2's latent space, which means that the output of our encoder always yields a realistic face. And so this means that we can allow ourselves to modify the images directly before encoding them, and hope to see this modification take a real value in the StyleGAN2 latent space. And so that's what we did. Here, for example, on the first line, we see how we dealt with the big nose attribute. Basically, we took the nose thanks to our semantic segmentation algorithm. We made it bigger on the picture. We encoded it, and then by adding background, we get the final image. And basically what we see is that the StyleGAN2 network is able to basically interpolate reality in our montage, which is interesting. Here we see that we did the same with the hair color. We just basically colorized the color in black, which made as an output more black hair that looked more black. And so if we zoom in a little bit, we see that here we indeed made some kind of collage, and this ends up being a realistic nose. Same goes for the hair. We see how we colorized some part of the hair, and there we see that we have realistic hair that looks blacker than the original. So we could use this method to find almost perfect vectors in StyleGAN2's latent space. So basically, we encoded this image on the left, this image on the right, took the difference, and if we add this difference to another image, we see that we have close to perfect modifications. So that's basically what we see on this video. With two images, we isolated a vector that is close to perfect for modifying the size of the nose, which was not done on this image. The vector was not isolated on this image, which makes this method really interesting. Now we'll quickly go over the methods we used. Well, the attributes we use this method on. So we use for big nose, pointy nose, bags under eyes, chubby, to make people thin and to change the hair color. So about pointy nose, we just basically drew a line on the nose, which made the nose pointier. But for flat nose, so the opposite of pointy nose, we find something that kind of worked. For bags under eyes, to erase the bags under eyes, we just whiten or made the areas under the eyes clearer, and to make the bags under eyes at their maximum, we just make them darker. And now for making people chubby, thin, we just lighten the cheeks, which made automatically people a bit less cheeky, basically. Now, eventually, we tried to do some reasoning on our methods, and this led us to make some choice in our submission for the competition. So, basically, in the E4E paper, so the encoder-frame editing paper, was already highlighted the trade-off between distortion and perceptuality, basically how the image globally looks realistic and how locally the image looks realistic. And we found out about a new trade-off that we call the reality-fidelity trade-off, which is basically the fact that if we want realistic images, we have to modify the overall context of the image, and so we won't match the original image. So that's what we see, basically. Here we see it bigger. We have the original image, the encoded image. We see that the background disappears, that the hat disappears. Now, if we want to try to add the hat using our semantic segmentation, for example, or the Photoshop method, we see that we already come up with some flaws here. The air just goes overboard the hat. And if we want to add even more fidelistic attributes like the background, we see that we get even more flaws, which is the fact that we see the two backgrounds overlap. So basically, there's this trade-off between fidelity and reality. And in our methods, we tend to choose the reality aspect of it, and using the properties of styleguide to have realistic photos. So that is the end of this presentation. We'd like to thank deeply Jules and Nicolas for organizing this competition, as well as the sponsors. We really enjoyed doing this competition and hope to see you on the next one. Bye.